Alright, welcome to the final lecture in this series on computer vision with OpenCV by Robotics by IITK. So I'll be talking about some more advanced topics in computer vision. So a brief overview. I'll first discuss interest point detection, which has corner detection methods, then Haar cascades for object detection, two methods for face recognition, which can also be generalized for other problems. Then a brief motivation on depth perception. Before I start, I just wanted to make a clarification between convolution and cross correlation. So, a convolution by definition is actually a transformation which is applied to a signal and it's defined by the operation star. While on the other hand, cross correlation is actually a similarity check for identifying similar patterns which can be shifted in time, for example, in the case of sound signals, or in space, for example, in images. So, what happens is in some fields, the term convolution is used for operations that are actually performing cross correlation. And this is something that needs to be kept in mind when we're going through literature significant to computer vision or other deep learning fields as well. Right? So, let's start with interest point detection. Interest points are local features which are associated with a significant change of an image property or several image properties simultaneously, like intensity, color, or texture. So imagine you have two different images which have different views of the same object, and you want to find the transformation from one view to the other. So these corresponding feature points help us to estimate the parameters which describe this geometric transformation. Interest point detection finds applications in image alignment, stitching, 3D construction, object recognition, image indexing, as well as object tracking and robot navigation. Uh, the process for IPD is that we first find a set of distinctive key points, define a region around each key point, and compute a local descriptor from this region, which needs to be invariant for rotation, scaling, translation, which can be accomplished with Q transforms. So once that is done, we match the local descriptors over different images, and the metric for this matching is cross correlation. The question here is what features should be used. So there is something known as the aperture problem, due to which edges cannot be used and therefore corners become an obvious choice. I'll try to give you some intuition about this problem. So consider that you can only view the motion of an object, in this case an edge or a corner, through through, uh, through a hole, right? So say you're viewing the motion of this edge, and you can't really determine the direction of motion or the motion vector of this line simply by viewing its motion through this hole, because you're not aware of what's happening at the end point. So if I'm moving it vertically or horizontally or in an oblique fashion, the motion that you notice inside this aperture or hole is exactly the same, right? However, on the other hand, if you consider a corner, then you can determine exactly what the motion of this corner is by observing it through this aperture. So this is where we have a notion of ambiguity in motion vectors. By observing some part of an edge, you can't really describe its motion. So you can't have an unambiguous motion vector, while for a corner you can. So let's continue with our first method of corner detection, which is Harris corner detection. Here, corners are identified as regions where there are large variations in the intensity of the gradient in all possible directions. Note that there are 8 possible directions. And we need to maximize this function E, which is given by the multiplication of the window function with the difference in intensities over all directions. So a window function is basically a weight given to the neighboring pixels when considering a particular pixel. You have seen the difference between a Gaussian window and a square window before. So what Harris corner detection does is it uses a Gaussian window which avoids discrete directions and shift. The algorithm for this method is that we first compute image gradients for all pixels and then determine the matrix M, which is defined here, It's the product of the weight for each pixel multiplied by their image gradient matrix. And from here, we calculate a response function, which is derived from the Taylor series expansion of the function e, which was shown on this slide. And here k is a free parameter which can be tuned. Right. So once the response function is determined, we find points with a large corner response function which is greater than some threshold. And then once we obtain the cluster of these points where the where the response function is greater than the threshold, we take points of locally maximum response as the detected feature points. I show you a short demonstration of Harris corner point detection with OpenCV. Let's see what the script does. And yes, so this was the original image car, and these are the identified corners in this image. So the background is pretty blurred, so no corners were detected there, but there's a fair number of corners detected on the car as well as on the gravel here. So what I've done here is I've taken an image and converted it into a single channel image and then performed the corner Harris detection. Once these corners were identified, I just simply superimposed these dilations onto the original image. Okay, so let's continue. The second algorithm is SIFT, interest point detection. So this is a scale invariant Fourier transform where feature detection is independent of properties like viewpoint, depth, and scale, which happens by transforming the data into scale invariant coordinates. I won't go into the depth of the algorithm, but it consists of four phases. Scale space peak selection, where the locations are pinpointed on the basis of whether or not the features hold true over multiple scales and hence passed forward accordingly. Then key point localization. This is similar to the thresholding that we saw in Harris corner detection, and the key points are accurately located, and the key points which do not um, conform to a certain threshold value or lie on the edge and are labeled as unstable key points are ignored. Then there is orientation assignment. Here, every feature is defined by some rotation function, so that or rotation function by defining its orientation, so that it becomes rotation. So these become rotation invariant when they're compared over different images or over different instances, right? And then there's the final phase, which is the key point descriptor, which finds a high dimensional vector representation of the key point by considering a neighborhood of say 16 by 16 or 8 by 8 pixels around that feature. So before we move on to the next segment, I would like to show you another example, which is on image stitching or panorama stitching. So what we'll be running here is a script which loads two images and finds the common points between those and then superimposes them to give us a combined image. So yeah, so these were the two original images, and what we've done with OpenCV's Stitcher class, Stitcher object, is that we found the common features in both these images and then superimposed them to find the panorama. Okay, so this was interest point detection. We'll now move to R cascades for object detection. Um, a brief overview of the theory. I am paraphrasing the 2004 paper which came up with the idea of R cascades. So this is a machine learning based approach which was motivated by the face detection problem. Its features are as follows. The images are represented by an internal image, which allows features to be used by the detector to be computed very fast. Then the learning algorithm does not use every single feature that it detects, but uses some critical visual features, which yields very efficient classifiers. And finally, the most important part, which defines the entire algorithm, is that we combine increasingly more and more complex classifiers in an array or cascade, which allows background regions of the image to be quickly discarded, while more computation and time is spent on promising regions which actually hold the object that we need to detect. So training is done with a large number of both positive and negative images, which are simply images which have objects which can be detected and otherwise. Okay. So this is how inference happens in a hard cascade. It's basically in the form of a decision tree, where a positive result from the current classifier triggers the evaluation of a second classifier, which has been adjusted to achieve very high detection rates. And as we go along these classifiers, the probability of actually getting a true value becomes very low. So what eventually happens is that only specific sub windows of the image where an object actually exists reach the final classifier and then go forward for further processing, while the windows of the image which hold no significance are are discarded very early. So I'll show you an example of face detection and eye detection with OpenCV. So what I'll be doing here is I'll read the video from the webcam frame by frame, and then uh, convert it to convert it to a single channel image on which these cascades have been trained. The cascades are XML files which can be found on OpenCV's GitHub repository. You can also make your own cascades for different objects. Right? So what I have used here are two cascades, one for frontal face detection and another for eye detection. These cascades give me the positions of the detected faces, their width and height, with the use of which I make bounding boxes on the face and a bounding circle around each eye. So this is how it works. So as you can see, my face has been detected very well, but my eyes haven't been detected so well right now because I'm not looking directly at the webcam. When I do that, it should be a little better. I think it was. Okay. So okay. So now we can move to the next segment, which is face recognition. I'll talk about two methods here: eigenfaces method and the Fisher faces method. Now, the eigenfaces method yields a lower dimensional representation of the image using principal component analysis. And once that lower dimensional representation is found, then the output is sent to a classifier which performs the face recognition. The basic idea here, and in the next method as well, is to minimize the variance within a class while maximizing variance across classes. Here, actually, a class-specific projection with linear discriminant analysis can also be applied and actually works better. We'll see one or two slides from now. So let's now consider the derivation of principal component analysis. Right. So we have a d-dimensional data point x, which can be represented as its projection over the basis vectors in those d dimensions. And we can reduce these dimensions from d to m by taking some m basis vectors and taking the projection of x over these basis vectors. Right. So we need to maximize the information that is retained in this transformation, and hence we need to minimize the mean squared error between these two data points. This can be represented as shown here. And if we consider that the basis vectors that we've chosen, ui, are orthogonal, then this can be reduced to a summation over the m plus 1th to the dth dimension of ui transpose over the variance S of the original data points into UI. Further, we know that these basis vectors are orthogonal and hence can add a constraint over their dot products. So we add a Lagrange multiplier, and over this minimization problem and take a derivative with respect to these basis vectors and find that this problem is actually equivalent to an eigenvalue decomposition of S. So the mean squared error eventually becomes the summation of the eigenvalues that we disregard in our uh, in our dimensionality reduction. So this is what the resultant algorithm for principal component analysis becomes. Given data samples S of n belonging to d dimensions, we normalize to find x of n, which are mean normalized from Sn, and then obtain the variance matrix S from these data points. Then, with eigenvalue decomposition, we obtain the eigenvalues in decreasing order and choose the corresponding eigenvectors as the principal basis for our reduced dimension representation of x of n, and take this as the projection of the original data points over these bases. Now, once these reduced dimension points have been determined, we feed these into a classifier for face recognition. The other method is Fisher Faces method, Fisher Faces method, which uses linear discriminant analysis. Now, the problem with PCA is that the discriminative info might actually be lost because the the variance over different dimensions might be from different causes like intensity or texture, which are not really relevant to a face recognition problem, right? So for this, we need discriminant analysis, which performs a class-specific dimensionality reduction. So in order to find the combination of features which separates best between classes, LDA defines a loss or error by the ratio of the interclass over the intra-class scattering, which instead of maximizing the overall scattering, which leads to an increase in the variance over different classes while a decrease over variance in the same class. So the idea here is that the same classes should cluster tightly together, while different classes stay as far as away from each other as possible. So, this brings us to the last segment in this lecture, which is on depth perception. We'll talk about both binocular as well as monocular methods of depth perception. So I'll first like to define binocular disparity, which is the difference in coordinates of similar features within two stereo images. For those who don't know, a stereo camera is a set of two cameras which are separated by a distance b, which is known as the baseline. For our current purposes, we'll assume that they have parallel principal axes, and hence we can derive the depth from the images captured from these two cameras as the inverse of the disparity of, of some feature or of corresponding features in these images. So, as you can see on the right, this can be derived pretty easily with standard trigonometry, right? I'll show you an example using image mapping. So we create a stereo PM class in OpenCV and then simply compute the disparity between two images. So disparity can be easily computed by performing interest point detection over the two images and finding the distance or the difference in the pixel distances of different features, right? And once this has been calculated, we can directly calculate the depth. So in this function, we have two parameters: the disparities and block size. So the block size is basically uh, the size of the neighborhood over which you calculate the features for disparity computation, and num disparity is basically the range over which we would consider the disparity for two features to be, or for a given disparity of the same feature to be of the same object, right? And then we compute the disparity image as a whole. So this is the depth image which was computed from two images that I'll show you now. Right. So These are the stereo images which were used to compute this map. So this is not actually a very good depth map in the sense that it does not show the exact depth differences in the different objects here, but it does give us a general idea of how the different parts of the image are closer to the camera or further away from the camera as the intensity or say as the intensity in the depth map or the disparity map changes, right? Right, let's move on. So this is monocular vision. Well, this happens to be a supervised deep learning problem. So there are many data sets present for monocular vision, which include the Kitty dataset, the NYU depth dataset, and the UASOL. So I'll talk about one of the methods, which is called monodepth 2. It's a self-supervised approach which uses monocular videos where consecutive frames provide the training signal, as in they provide some correlation between two consecutive images. Now, the model also needs to estimate the camera pose between frames, which becomes a challenging task in the presence of object motion. Monocular vision is based on a reprojection error, which is the geometric error corresponding to the image distance between a projected point and a measured one. What we practically do here is that we estimate some 3D uh, location of a certain feature and then try to recreate the image on the basis of that location, and then compare the actual image with this generated image to see whether or not our prediction was correct. So I'll be directly using an example from the monodepth repository. Uh, so here what they've done is they will load the model, which is a monocular model, which consists of two networks, an encoder as well as a depth decoder. Now, the original image is this, and the resultant disparity prediction is this. Now, we can see that this is actually a much better disparity map than what we had last time. So, can be attributed to the fact that we were only basing our disparity map in the previous example on the inverse linear relationship between depth and disparity without actually knowing the focal length or the baseline distance between the of stereo camera which is used to capture these images. Uh, However, in practice, when we use a stereo camera, we obviously know all this information by calibrating those cameras, and hence can obtain very accurate depth maps. As an exercise, I would suggest you to try the stereo vision modules in ROS, which I think you've learned now. And that brings us to the end of this lecture. Thank you.